Okay, so what are hypothesis tests? Hypothesis tests are nothing else than ways that we run, tests that we run in order to calculate confidence intervals and approximate the measures, the population parameters for the different measures that we want to work on, either the mean or the standard deviation or the variance, anything that we want to work with. Hypothesis tests in general have 8 points, eight different steps. And if you try to memorize, many of my students, especially the undergraduate students that they haven't seen statistics before, what they try to do is they try to memorize the steps. This doesn't work. You really need to understand why you take each one of the steps. If you try to memorize the steps, and for each case, I can assure you that you will have to memorize 48 different tests. And this is impossible to memorize them. If you understand what you do and why you take a specific step for any problem that they give you, then it will be much easier and you will have specific cases to remember, to memorize for each one of those steps. So, the hypothesis test. The first thing that you need to remember is that you start with a claim. The claim, it's going to be a sentence, and a sentence in English that is a claim either that you make as a statistician, as a data analyst, or that is given to you by your manager or by your customer, whoever is that needs you to complete the data analysis. So the claim is a sentence, a statement that somebody believes that is true for the specific measure that you're working with. Now, the claim has a complement. The complement of the claim and the claim itself are two statements that the one is the opposite of the other, and they complement each other. And these are the ones that we set as null and alternative hypothesis. Let's see. The null hypothesis, the one thing that you need to remember is that the claim the claim can be either the null hypothesis or the alternative hypothesis. If the claim includes an equality symbol in any form, less or equal, greater or equal, then the claim will become the null hypothesis. If the claim doesn't include the equality, then it becomes the alternative hypothesis. No matter what you do, though, no matter if the claim is or it's not the null hypothesis, your test will run on the null hypothesis. So these are two things that you need to remember. For example, you end up having, after you have your claim and you translate your claim to either null or alternative, assume that you're running a test on your mean. The three different cases that you may have are the ones that you see in red right here. These are the sets, the pairs of null and alternative hypotheses. As you can see, each one of those pairs are sentences, statements that are complementary. The one complements the other. Either the one or the other will be true. As you can see, the null hypothesis in all the three cases include the equal sign, while the alternative hypothesis never includes the equal sign. Now, depending on what your claim is, your alternative hypothesis and null hypothesis will be one of these cases. An example, a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. Now, if you read this, let me see. Yes, very good. Very good advice. If you read this carefully, you will see that this is a statement that no one will give, not even a school will publicize such a statement. It's a very strong statement. What does it say? It says that the proportion of each student, so the proportion of the students in the school that are involved in at least one extracurricular activity is exactly, since it says is 61%, then it means that it's exactly 61%. The question here is who cares? A school, if they want to claim something like that for advertisement, they would say at least 61%. At least 61% of my students are involved in at least one extracurricular activity. This is the right statement. This is the statement that would advertise a school. But in any case, let's look at this, assume that this is the statement that the school gives. In this case, as we can see, the claim is clear. The school says that the proportion, the P of the students, is equal to 61%. So this means this is the claim, and since the claim, it includes the equality right here, then this means that it will become the null hypothesis. So once you have the claim, you have either the HO or the HA. In this case, the HO. Once you have the HO, then immediately you can create the complement statement, as Advaita said, mutually exclusive and collectively exhaustive. You get the alternative hypothesis, that is, the proportion of the students that are not involved in, that are involved in at least one extracurricular activity is not 61%. This is the complement of HO. And this is how you set up the pair of the null and alternative hypothesis. In this case, the claim will be the HO, and the HA will be the opposite, the complement of the claim. Now, no matter where the claim would be, in HO or in HA, your test will run on HO. Another example is right here. A car dealership announces that the mean time for an oil change is less than 15 minutes. Now, this is a meaningful advertisement. Yes, I want to advertise that in my shop, the time that you need to spend waiting for oil change is very little. So it's less than 15 minutes. Now, immediately you can see that the claim doesn't include an equal symbol. And since it doesn't include an equal symbol, this means that the claim will be the alternative hypothesis. Now, the HO is going to be the mean is greater or equal to 15 minutes. Remember that again, in this case, your test will run on HO. Now, as we were discussing before with David, we have two different types of errors. At the end of the test, we run the test for the HO. We reject or fail to reject the null hypothesis. And it is possible, based on the confidence level that we have running our test, to be wrong, to have a wrong result, an incorrect result, an error. So this means that we have two types of errors. Either the null hypothesis is true and we reject the null hypothesis, and in this case we have a type 1 error, or the null hypothesis is false, but we do not reject it. In this case, we have a type 2 error. Okay. What I want us to see right here, let's see this example. The USDA limit for salmonella contamination for chicken is 20%. A meat inspector reports that the chicken produced by a company exceeds this limit. You perform a hypothesis test to determine whether the meat inspector claim is true. When will a type 1 or type 2 error occur? Which is more serious? Okay. The hypothesis that I have is that the proportion is less or equal than 0.2. The claim of USDA is that the proportion is greater than 0.2, is greater than 20%. Okay, so the limit that USDA gives us is 20%. We do not want to have more than 20%. So the alternative hypothesis is going to be that the proportion is greater than 0.2. The null hypothesis will be that the proportion is less or equal to 0.2. Now, if we run a test on that, we have the hypothesis, we have our claim, and we can see right here that the type 1 error is when we reject the HO, when it is true. What is the HO? The HO will be that the actual proportion is less or equal than 0.2. This means that is under the limit of USDA. And you reject the HO. The type 2 error, it will be exactly the opposite. The actual proportion of the chicken is greater than 0.2, but you do not reject the HO. In the specific example, you can see that the type 2 error is more serious. And it's more serious because you will allow to a quantity of chicken to go out, although the proportion of the chicken that is contaminated is greater than the USDA limit. And this is worse than destroying part of chicken production, even if the contamination is under the limit. Okay, it will cost some money, but it's not going to cost any lives. The type 2 error in this case will cost lives. Is this the case for all the type of problems? No. We have situations where the type 1 error is more serious than the type 2 error. So there is no way to say that it really depends on the test that you're running. It really depends on the analysis that you're running, which error is more important for your case. There is, though, belief that type 1 errors are worse than type 2 errors, especially for scientific reasons. They are more serious. Okay, so after you set up, when you run your test, your HO and your HA based on the claim, the next thing that you want to do is to know what is the level of significance for your test. The level of significance is basically the alpha. The alpha is nothing else than 1 minus the confidence level. The alpha is nothing else than the area of the tails. Why the area of the tails is important? Why do we call it the level of significance? Remember that the rejection area usually is on the tails. For example, for a two-tailed test, the rejection area falls on the tails. So the alpha is the area of the rejection, is the rejection area, especially for a two-tailed test. So for a two-tailed test, alpha is the area of rejection. For a left-tailed test, alpha again is the area of the rejection. For a right-tailed test, the alpha, 1 minus alpha, will be the area of the rejection. We have different types of statistical tests, depending on the measure of the population, or the population parameter that we test. We can test the mean, the proportion, the standard deviation, or the variance. No matter which parameter we test, at the third step of our test, we are going to calculate the test statistic. What is this test statistic? The test statistic is nothing else than the score, either the z-score if we run a normal distribution test, or the t-score if we run a student distribution test, or the chi-score if we run a chi-square distribution test, that will represent the specific x, the specific variable that we are working with, and it is given by our sample. P-values. What do we call p-values? P-values or probability values is the probability that the sample statistic is at the extremes. The probability that the sample, of where the sample statistic lies on the bell curve, if we are talking about a normal distribution or student distribution, or under the curve of the chi distribution. I want us, though, to look into a specific example to see the relation of the p-values with the critical values that we learned last week on our confidence interval. When we run a test, after we set up with our hypothesis, with our claim, the null hypothesis and the alternative hypothesis, we end up having either a left-tail test, a right-tail test, or a two-tail test. We have a left-tail test if the alternative hypothesis is less or equal. A right-tail test if the alternative hypothesis is greater. And a two-tail test if the alternative hypothesis is different. So if you go back to here, after you set up your claim, and using the claim you set up your pairs of hypotheses, if you end up to having the first pair of hypotheses, then this means that you have a right-tail test. The middle one gives you a left-tail test, while the third one gives you a two-tail test. So the type of test you have is declared by the alternative hypothesis. Greater gives you a right, less gives you a left, different gives you a two-tail test. Let me go back where I was, right here. So, the left-tail test, when you run the left-tail test, you have your hypothesis, your null hypothesis and your alternative hypothesis, and you have the bell curve. Assume that you have a normal distribution. Then one thing that you need to remember right here, oops, where is it? I'll just try to move this blue area. It doesn't allow me to. Anyway, what you see right here on your screen is the bell curve. Since the test that you have is a left-tail test, because it has less or equal, then a left-tail test means that your rejection area is going to be on the left tail. So the left tail, the blue area right here, is going to be your rejection area. What is the relation of this rejection area with your alpha? Well, your rejection area is your alpha. So the proportion of this blue area to the entire bell curve is going to be as much as your alpha says. Your alpha is your significance level. So if your alpha is 0.1, so 10%, then this means that your tail right here, that is your rejection area, is going to be 10% of the entire curve. So alpha significance level is the area of your rejection region. And the rejection region for a left tail test is always to the left tail. In the same way, the right tail test, that is denoted by this, we will have the rejection area to the right side. It's going to be the right tail. And again, it is equal to your alpha. Now, coming to a divide question, if you have a two-tail test, then this means that you have different than K, your alternate hypothesis, then this means that your rejection areas are going to be splitted left and right of the entire bell curve. So you will have two rejection areas. Half will be on the left tail and half will be on the right tail. Half of what? Half of your significance level. What is your significance level? Well, if your confidence level is 99%, then your significance level is 1%, meaning 0.01. If you have a two-tail test, then this means that each one of these regions, the blue regions, the rejection regions, will be 0.005, meaning 0.5% of the entire area. Okay, now what's the relation between the alpha, the type of the test that you have, and your p-value? Well, the p-value is going to be nothing else than the probability for your test statistic. What is your test statistic? Your test statistic is the score of your x, whatever the x is, your variable that comes from the sample. Once you calculate that, you find the probability, that is nothing else than the area to the left of that x. If you run a left tail test, your p is going to be somewhere on the entire area right here, anywhere from negative 3.33 to positive 3.33. If your p, I'm talking about the critical values here. The p is going to be anywhere from 0 to 1. What you compare now when you look at your p-value, the p-value is compared to your alpha. Your alpha is right here. If your p is greater than your alpha, then this means that your p will be to the right of the blue area. So it's not going to be in the rejection area, it's going to be in the non-rejection area. This is how we compare the p-value with our rejection areas that are the alpha. In the same way, when we have a two-tail test, again, we calculate the p the same way, but now our alphas are splitted into halves. So the p that we get from our x needs to be twice the area from left to right, because we have half of the area of the rejection area to the left and half of the rejection area to the right. Okay, let's look at an example. We have seen this example. This is only to set up the problem. Let me run an example from starting to finishing. Where is it? Here. In an auto racing, a pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds. A random selection of 32 pit stop times has a sample mean of 12.9 seconds and a standard deviation of 0.19 seconds. Is there enough evidence to support the claim at alpha significance level 0.01? We want to use the p-value method. We have two different methods of running tests. Either we use the p-value method or the critical level method. We are going to run one test for each one of these methods together. For now, I want us to do it together. So I don't want to explain everything. I want you to tell me. Looking at this problem right here, the first thing that I want us to say is, what is the claim? The claim is that the mean value for the stop time is less than 13 seconds. Less than 13 seconds means that the claim doesn't include an equal sign. Since it doesn't include an equal sign, then this means that the claim will become the alternative hypothesis. And the null hypothesis will be greater or equal to 13 seconds. Very good. Yes, that's right, exactly. So that's the one thing. And we have finished with step one. We set it up. We set up the HO and the HA. Now the next step is a random selection of 32 pit stop times. Let me stop right there. What information do you have right here? You have 32 different stop times in your sample. What does this mean for you? Very good. N is greater than 30, and based on Ken Black's book, greater than 30 means that we can use the z-test. Now, as I explained last week, this is only for instructional purposes. We cannot assume always in data analysis that if the n is greater than 30, we use the z-test. For now, we are going to use the normal distribution because 32 is greater than 30. Now we have a sample mean that is 12.9 and a standard deviation of 0.19. Since our sample size is greater than 30, then immediately we can use the normal distribution. If the sample size was not 32 and it was 28, then we would have, even with Black's book, we would have to think before we continue. If the number is under the 28, if the sample size is under 30, then we need to know one more thing. If we know the standard deviation of the population, then we can still continue with the normal distribution. If we don't know, though, the standard deviation of the population, then if we have a sample size less than 30, it means that we have to use the student distribution and work with degrees of freedom. Now, one thing that I want to make sure that you understand is that when this says sample mean is this and standard deviation is this, it refers to the standard deviation of the sample. Knowing the standard deviation of a population is extremely rare. We very rarely know the standard deviation of the population. So, what we have until now is the claim, the HO, and the alternative hypothesis, and the fact that we are running a test using normal distribution. We also know that our alpha is 0.01. Going back to the claim, less than 13 seconds, and this becomes the alternative hypothesis, this immediately means that our test is a left tail test because the HA is mean smaller than 13. So it is a left tail test. What we have until now is null hypothesis, mean greater or equal to 13 seconds. Alternative hypothesis, mean less than 13 seconds. My significance, alpha, 0.01. Left tail test, because I have a less here. This means that my rejection region will be at the left side, at the left tail of my bell curve. Okay. The next step that I have to take is to calculate the test statistic. The test statistic, since I ran the test with normal distribution, is going to be the z-score. How is it calculated? In the same way, using the same formula that we used last week to calculate. No, actually, we didn't use that last week. The test statistics are different depending on the parameter of the population that we want to calculate. When we refer to the mean, the test statistic is calculated with the formula that we used 3 weeks ago in order to find the z-scores. So we have the x bar, that is the point estimate, minus the mean, that is the hypothesized mean for the population, divided by the standard deviation of the sample, divided by the square root of the sample size. Negative 298 is the number that we calculate using this formula. Okay, so we calculate the z-score, negative 2.98. We expect, of course, the negative 2.98 is almost 3 standard deviations to the left of the mean in the bell curve, right here somewhere. But we want to know if this negative 2.98 is in the blue area or in the pink area. If this number right here, this is the test statistic, if this number right here is in the blue area, we are going to reject the HO. Why? Because this number right here, that is the z-score, the corresponding z-score for the x bar, for our sample, will fall in the rejection area. If the negative 2.98 is not in the blue area, then it's going to be in the pink area. So it's not going to be in the rejection area, and we will fail to reject. So depending on where the negative 2.98 is, in the blue area or in the pink area, we either reject or not reject the HO, the null hypothesis. Now, at this point is where we know that there are 2 different ways, 2 different methods to actually continue my test. The one method is using the p-value. The other method is using the critical values. What's the difference? Well, if I have my z-score, negative 2.98, and I use what Pvalue told us, p-norm of negative 2.98, then this will give us the probability for the corresponding score. So it's going to give us the area to the left of that score. If the area, so the p-value is going to be nothing else than the area from the negative 2.98 to the left. If this number is greater than the region, than the rejection region, that is what? Alpha. This is what the blue region is the alpha. So if the p-value is greater than the alpha, then we are going to not reject, because the negative 2.98 will be on the pink side of my x-axis. If the p-value, meaning the area that corresponds to this number, is less than 0.01, then this means that the area of this number will be somewhere here, less than the blue area. So if the p-value is less than this, then I will reject my HO. Why? Because this number right here will fall in the blue area. Then the result that I will get will be 0.0014. 0.0014 is less than 0.01, and this means that I will reject my null hypothesis. Am I done? Yes, I'm done with my test. I ran the test and I have my result. The result is reject the null hypothesis. But is this the answer that I can give? No, this is not the answer. When we answer, we have to answer on the claim. By rejecting the null hypothesis, we don't know what we do with the claim because we don't know what the claim is. We have to go back and remember what the claim is. Well, as you can see right here, the claim is less than 13 seconds. So the claim is the null hypothesis. This is the claim. Oops. Let me make it bigger. Okay, so if I reject the null hypothesis, that is the top, then this means that I do not reject my claim. So the result that I get from this is that I do not reject the claim. So what does this mean? This means that I have reasons to believe, meaning I have sufficient evidence, that the claim is correct. So I have sufficient evidence to conclude that the claim, the mean stop is less than 13 seconds, is correct. 13 seconds is correct. How do I phrase that? I phrase it always including the level of significance in my conclusion. So with 1% level of significance, meaning with 99% confidence level, I have sufficient evidence based on the specific sample to conclude that the claim that the mean is less than 13 seconds is correct. The conclusion should fit with the claim, not with the null hypothesis. These are asymmetric distributions. Based on the CTL, the central theorem, any distribution that you have, it is possible to transform it, to take sampling distribution of that and transform it into normal distribution. So you will take the mean of the means, and the mean of the means with the standard deviation being the standard errors of your samples will give you the normal distribution. But how big of sample size can you have? Well, this really depends on the type of the distribution that you have. Looking at the examples that you have right here I have chi-square distributions, a chi-square distribution, but I don't have any outliers. Right here I have chi-square distributions, but I have a lot of outliers. Okay, so what happens right here? Can I create sampling distribution from those? So take samples from those with let's say 30 different sample points, and assume that I can use the normal distribution in order to run the test. Well, maybe for the top one, but not for the bottom one. The bottom has outliers, and if you look at, where is it? Here. If I have samples of size 40 from the first one, I have this. This is my result. And what you can see right here is that I have outliers. I have outliers. This is not a perfect normal distribution. Same thing happens right here. The outliers are on the left. So in the lows that you see that you have points that are going away from the line. What does this mean? This means simply that if I take the same distribution that I show you above, the asymmetric distribution that I show you above, but now instead of taking the sample size of 40, I take a sample size of 150. Then the histogram that you will see right here will be more similar to a bell curve. And if you go to 200, you will go even closer to a bell curve. What does this mean? This simply means that the bigger the sample, the closer that I go to the normal distribution, so I can assume normality and I can run my tests using the bell curve. So going back to the example that I showed you, the method that we just saw is using the p-value. So this is what we do with the p-value. We calculate the p-value and then we check the p-value with the alpha. Why the alpha? Because the alpha is the rejection area. If the p-value, that is the area to the left of this number, is greater than the alpha, then I reject. I don't reject. If the p-value is smaller than the alpha, then I reject. And this is the case right here. But this is something that happens only for a left tail test. Why the left tail test? Because the left tail test has the blue area right here. If it was a right tail test, the blue area would be here. So once I calculate my p-value for a specific number like this, then I have to take 1 minus the p-value, 1 minus the probability, and compare it with the blue area. So do I have an example? I think I have an example of that. I don't have an example of a right tail test, but I have a similar example for a two-tail test. That's the example. Again, it's a normal distribution because I have 30 bariatric surgery patients. Again, the test that I ran is on the mean. Again, now this time is on the price of the surgery. And again, I want to run it with a p-value. If I set up my test, I see that the HA is different than 22,500. So I don't care for the test right now. What I want you to see is the p-value. I run the test, I calculate my test statistic, I find my test number. The test statistic is negative 1.73. Now, the area to the left of the number that I will get is going to be the p-value. So the area to the left is going to be the 0.0418. That's the number that I will get. But now, I want to know where this number stands. Since my alpha is 0.05 and my alpha to the left is half of the 0.05 and the alpha to the right is alpha half, so it's 0.025. What I compare is not the area of that with this, but the 2 times the area of that with this. So I compare the p-value, the 0.0418, that is the area that corresponds to this z-score. I multiply this by 2, and then I compare that with my alpha. Why? Because again, what I want to say is that if the area that I get for the z-score is on the pink area, and if in order for this to be on the pink area, it must be greater than half of that. So I need to multiply this by 2 and compare it with this. In this case, the number is greater than 0.05, so I fail to reject the HO. My claim is, what does it say? I think that the information is incorrect, so I think that the average cost is not 22,500. So my claim is the alternative hypothesis. I fail to reject the HO, so this means that I reject the HA, so I reject the claim. So at 5% level of significance, meaning with 95% confidence level, there is not enough sufficient evidence to support my claim. And that will be my conclusion. Now, in both of those examples, we ran the test with a p-value. But I said that there is another method as well, and the other method is called the method of the critical values. What are the critical values? I want to remind you that we saw them last week. The critical values are nothing else than the z-scores of those lines that separate the rejection area from the area inside the confidence interval. So the critical values are the z-scores right here and right there. If I want to run the same test with the critical values, then what I need to know is what are the numbers right here and right there, and compare those numbers with the negative 1.73. Why? Because negative 1.73 is the z-score of my x bar. By being a z-score, this means that negative 1.73 is somewhere here, right here, between negative 2 and negative 1. Now, what I need to know is where exactly is this number. Is it in the pink area, in the pink segment of the x-axis, or in the blue segment of the x-axis? Well, as I said, it's negative 1.73, so it's going to be somewhere here. Now, if I know what this number, the z-score that corresponds to the border of the blue region is, then I can compare the negative 1.73 with this number right here. Now, the z-score for the critical value is going to be nothing else than the z-score of your alpha. Your alpha is 0.05, but you have a two-tailed test. So alpha half is what you have on this side, and alpha half is what you have on this side. So if you find the z-score that corresponds to 0.025, then this will be this number right here, 0.025. And I can assure you that the number right here, it will be negative 1.96, and the number right here will be 1.96. Now, since you have a two-tailed test, if the test statistic is between the critical values, then this means that it will be in the pink area. So you do not reject. If it is greater than the highest critical value or smaller than the smaller critical value, then you're going to have this number to be in the rejection areas, either here or there. So you are going to reject. So in order to calculate the test statistic for mean, you get this formula. The way to get the test statistic for the proportion, do I have the proportions here? You get this formula where the p hat is going to be the point estimate for your sample minus the proportion for the hypothesized proportion for the population, divided by the square root of PQ divided by N. Remember that this, the square root of that, is nothing else than the standard deviation of proportion. And the only thing that differs every time that you decide to run a test for a different parameter is the formula that gives you the z-score or the t-score. And that's it. And if you run the test for standard deviation, and I have here on the notes a test for the standard deviation, the chi-square test, the formula to calculate the chi-square is going to be n minus 1 times the standard deviation of the sample square divided by the standard deviation of the population square. And that's it.